welcome back. So today we will go into the details of the casting processes. So in the last class we have discussed about 10 rules of getting good casting of metals and composite specimens. So what is casting? So it is basically the process in which the liquid melt is allowed to solidify in a predefined mold cavity. After solidification, by breaking the mold, we basically derive the shape of the object that we achieve by solidifying the liquid melt. So, the advantages of casting process are it is a versatile process. So, any shape can be manufactured by casting route, and also there are several complex shapes which are otherwise difficult to manufacture, or it can be manufactured by casting in a economical manner, and it is very large size objects like that of used in power plants or machine tool bed, road rollers, etc., can be manufactured with relative ease by casting route, and it is useful technique for mass production. However, there are certain limitations with the casting process, such as the mechanical property is not up to the mark compared to that what we can achieve in case of forging technique, and also it is a sometimes for sand casting, if we are talking about, then it can be a labor intensive and time intensive process, and also because surface finish and dimensional tolerance is not up to the mark compared to the again extrusion based processes. So, and another important difficulty that we face in case of casting is that non uniform cooling of different sections, and which leads to the different mechanical properties, inhomogeneous mechanical properties at different cross section of the cast parts. So, these are the limitations. So, so these are some of the typical components that can be manufactured by melting casting route. It encompasses several industries. So, starting from automotive to aerospace, and also mining industry, and electronic industry, defense. So, there are several applicability of the melting casting technique, and so there are some examples which are given over here, like turbine blade, power generators, mill housings, railway crossings, etc., and some other like supercharger casting out of magnesium alloy, pump, filter, valve, aircraft, jet engine blades, which are generally manufactured by directional solidification route. Even single crystal castings are also achievable. We will discuss about it later in the course, and then sanitary fitting, communication, construction, and atomic energy application based components are also can be manufactured by melting casting route. So, so these are the steps involved in metal casting. So, number one is pattern making. So, basically what is pattern? Pattern is nothing but the replica of the end component that we want to manufacture by the melting casting route. So, accurate pattern making is essential to get the desired shape of the mold cavity, to achieve the desired geometry of the cast part, and then the second step is molding and core making. So, if for example, if we talk about sand casting, so then the pattern is needed, and then we need to ram the sand so in a at the periphery, so that we can get the desired mold, and also that mold has to have sufficient strength, structural integrity, so that it can withstand the metallostatic forces that is exerted by the liquid melt when it is allowed to be filled within the mold cavity for and subsequent solidification. So, so these are the attributes that are necessary. So, that is why it is very much essential to choose the appropriate mold material for the particular job in hand. So, like if there is very high surface finish is in demand, then we can definitely go for metallic molds, and if there are very large components where there is a significant amount of machining and other allowances are kept, then we can go for sand casting, which will become more economical in that case. And also another important part is the core. So, core making is also equally important, because core is the so for example, if you have to make a hollow casting, and there are some certain cores which are present in that casting. So, then these are basically the hollow cavities within the cast part can be achieved by developing appropriate core. So that core are generally made by a different grade of sand what generally we generally used in case of mold making. So because the core needs to have a higher mechanical strength than the mold itself, because it remains in the condition it's because based on its location that we will discuss later on. It can be hanging, it can be present as a cantilever beam within the mold cavity. So that is why it needs to withstand significant metallostatic forces. So that is why the core sand material being used for core making, and also the binder ingredients to adhere to the to keep the sand particles in adhered condition is of utmost necessity. So this is the second step of casting, that is molding and core making. And then the third and one of the most critical step is the melting casting. So it is in melting casting, the most important thing is the melt preparation. So as I told you in when I have discussed in the last class about the that is the first prerequisite of out of 10 thumb rules of getting good castings is the in appropriate melt preparation. So so the melt which is going to solidify in the shape of the component, that needs to have the appropriate chemical composition that we want to get in the cast part, and also it should be free from dirt inclusions which can otherwise cause defect formation in the solidified part. So that is why melting casting is the third one of the most important step in the casting process. And then fettling. So what is fettling? Basically, like we have discussed in the last class also, that a typical casting deals with the mold getting arrangements, and also runner, riser, and also the pouring sprue and all. So these are basically the analogous parts which are non-functional parts after solidification. Of course, they are the functional parts during the melting melt preparation process. So for example, if we are casting a shape like this, so this is basically the sprue, and this is the runner, and this is the ingate. So these are basically the functional parts. So this is the sprue base well. So these are the functional parts during the feeding of the liquid melt. So because they basically causes preferential melt flow within the component cavity that we are intending to cast. But once the solidification is done, so then this is only our functional part, that means the solidified component. So these all three parts need to be strike off. So the process of machine them out after the casting is done is called fettling. So it is also an important step in the casting process, because it is necessary to remove them effectively, and also it should not end up making a notch over the cast object, because then that can serve as a preferential site for crack nucleation and fatigue failure, provided the component is subjected to fatigue loading. So that is why fettling is the another important step of casting process. And then testing and inspection. So once we have got the cast object, then before deploying it to in service conditions, we need to inspect it. So there are several destructive and non-destructive testing techniques available for that. And so like dye penetrant test, like magnetic particle test, like X-ray radiography. So these are different non-destructive testing techniques that we employ to see that whether the cast object is of sufficient structural integrity, and whether the whether it will yield uniform deformation behavior when subjected to in service conditions. So this is one of the last and critical step in casting to deploy the component in service conditions. Okay. So now we will start with the casting terminologies. So these are the different functional parts of a typical mold cavity. So number one is the flask. So it is the it is made of metal or wood frame. So it consists of two molding flaskes. So one is placed at the bottom, another is placed at the top. So here the bottom flask is called the drag, and the top flask is called cope. Okay. So, I mean, so this is the example is being given in case of a typical sand casting mold. So, you can understand from here, so that the cope and the drag fluxes, flux can be prepared with the molding sand for mold preparation by two different persons altogether, and then they can be joined along this parting line. So, that is how we can we can fast track the mold making process, and and also we can save a lot of time. And number 2 is pattern. So, as I told you earlier, so pattern is the replica of the final object that is going to be developed by melting casting route. Generally, it is made of wood, but there are cases where we also use metallic patterns when there is a mass production is involved, and pattern can experience wear and tear due to repeated use. So, that is why we can also go for metallic patterns. Number 3 is the parting line. So, parting line is the line which differentiates between the two molding class, that is cope and drag. So, this is basically the parting line that we have we just need to go back to So, we are back to the slide. So, this is basically the parting line which divides between the cope and drag flasks. So, that is called the parting line, and then the molding sand. So, the sand grains which are used here. So, you can see the sand grains over here. So, this is basically called the molding sand. So, the molding sand should be of sufficient quality, it should be free from moisture, so that it should not cause the this gaseous emissions, and thereby which the gases can be trapped within the mold cavity, and that can cause blowholes and also gas porosity within the solidified cast part. So, that is the molding sand, and then there comes the facing sand. So, facing sand we generally use for to sprinkle at the boundaries of the after placing the pattern and ramming the mold around it. At the top of the pattern we sprinkle the facing sand, so that the this is basically marks the surface of the of the cast object. So, so that we can get a desired improved surface finish, so that we can out of the cast objects. So, this is the essence of facing sand. And then core. So, a separate part of the mold made of sand and generally baked, which is used to create openings and various shaped cavities in the castings. So, we have already discussed about core. So, here, so this is the typical example of core in this mold cavity. So, which is needed to create a hollow section within the cast part. So, going ahead with the different casting terminologies. So, number 7 is pouring basin. So, pouring basin is basically a small funnel shaped cavity. So, that is at the top. So, this is basically the pouring basin. So, it is kept at the top of the mold into which the molten metal is poured. So, it has multiple roles. So, pouring basin sometimes can also be like this. So, this is also serves as a pouring basin. So, here you can see that it can be useful to trap the dirt or inclusions, unwanted parts which are present in the liquid melt. Even after careful melt preparation, there can be some unwanted objects or inclusions which can get trapped in the mold pouring basin, and so that they doesn't allow to get into the mold cavity by the pouring sprue. So, that is the essence of pouring basin, and also it also helps in reducing the turbulence, the velocity of the liquid melt, so that it flows through the sprue in a laminar fashion, and so the melt flow rate can be controlled, and thereby chances of turbulence and gas absorption within the liquid melt can be minimized. So, number 8 is the sprue. So, basically this is the sprue, that is what I have drawn over here as well. So, this is the sprue. So, what is the function of sprue? So, this is the passage through which the molten metal from the pouring basin goes through to the mold cavity. Generally it discharges the liquid melt to the runners, which then later on transport to the ingates. So, that number 9 is runner. So, like I told that it carries the melt from sprue base well. So, this is basically the sprue base well. so from here we the runners transport the liquid melt to the ingates of the cast objects. So, this is basically the ingate. Okay. So, a channel through which the molten metal enters into the mold cavity. So, this is basically our desired cast object cavity. So, there this is basically the last passage the liquid melt travels through the gating arrangement to enter into the desired mold component cavity, and then chaplets. So, chaplets are basically used to support the cores. So, like I have already told you, so this is the core. So, that core has to be supported with the help of chaplets, so that it can take care of its own weight and also can overcome metallostatic forces. And then riser. So, riser is basically kept like a reservoir which is necessary to feed the solidification shrinkage the solidifying component is undergoing. So, as I already explained that the solidification shrinkage happens due to the density difference between the liquid and the solid of the same material, and the riser is the essential part of the mold cavity to feed to that solidification shrinkage. So, it is also called feed head or feeder head. And then vent. So, vents are small openings in the mold to facilitate escape of the liquid air and the gases, those are evolved during interaction of the liquid melt at high temperature with the additives which are generally used for mold making, and also additives which are generally used for core preparation. So, the moment they come in exposure to the high temperature liquid melt, they starts to evaporate and form gases. And also there are some, like for example, non-ferrous alloys like aluminum, there is chances of entrapment of hydrogen. So, the hydrogen solubility also decreases as the melt solidifies. So, that escaped hydrogen and also the gases evolved during at the exposure with the liquid melt. So, these gases can escape through these vents, so that we can get desired level of structural integrity in the castings. Okay. So, then now we will go into the part by part of several functional parts of the gating geometry and the casting important parts of the casting process. So, pattern may be defined as a model or replica of the object to be cast. So, only variation according to dimension between casting and pattern are the various allowances. So, so there are several allowances that we provide to the patterns for different reasons, such as shrinkage allowance, draft allowance, machining allowance, and also shake allowance, and so on. We will discuss one by one of all those allowances. So, this is the as I told earlier that the sand is packed within the molding flux. When we are talking about sand casting, because that is one of the basic casting technique. So, we are all taking the example of sand casting again and again. So, sand when it is rammed around the pattern and after its removal mold cavity is formed. So, in which molten metal is poured to achieve the final cast product geometry. So, the difference between the pattern and casting. So, main difference between pattern and casting is their dimension. So, as I told already that pattern should be larger than the casting to accommodate for the shrinkage happens in the during solidification. That is the combination of liquid shrinkage, solidification shrinkage and solid shrinkage. So, these are larger in size. So, and also it should be larger to accommodate for the draft allowance for tenal and internal surfaces and as well as machining allowance. So, pattern also carries core prints. So, these are also necessary to support cores within the mold cavity, and pattern can be made of single or multiple pieces based on the particular application or the component going to be developed. And so the material used for pattern is generally wood, sometimes metals, but the cast metal is material what is going to be solidified by the casting route are entirely different than the pattern. So, the function of pattern, what are the functions? So, it produces mold cavity in sand, its casting has a core pattern contains core print. So, number one is basically to achieve the cavity, mold cavity, so that we can get the shape of the solidified component. Number two, to support core prints. Number three, it defines the parting line and parting surfaces in the mold cavity, and also properly made patterns provide finished and smooth surfaces to casting to reduce their defects. And then number 5 is properly constructed patterns reduce the overall cost of the process. So, these are the functions of the pattern. So, now we will go about the patterns, we will discuss about individual type of pattern. So, number 1 is solid or single pattern. So, it is the simplest of all patterns is made in one piece and it has got no joints. So, in this case partition or loose pieces are not there. So, in this case the pattern is kept in one of the molding flask, like either it is kept in cope or it is kept in drag. So, because there are no two pieces, so there is no need to keep it in two different flasks. So, since its molding involves many manual operations like gate cutting, providing runner and riser. So, such patterns are used for producing a few large castings, for example, stuffing box of steam engine. So, what is the so here difficulty in case of single piece pattern is that we are only getting the mold cavity out of the pattern. So, for example, that this is a typical pattern that of the cast object that we have made. So, this is the only shape that we are getting from the pattern, but all these other sections, that is the sprue, runner, ingate, that need to be constructed within the mold cavity. That means, if you are going using sand mold, then we need to create by hand tool or some appropriate device. So, these are not integral part of the pattern itself, and whereas in the second variant is split or two piece pattern. So, here the molding process can be time can be decreased, because in this case the one half of the pattern remains in the cope flask and the other half of the pattern remains in the drag flask, and we can basically ram the sand at their periphery simultaneously, and thereby we can achieve the two halves of the mold cavity simultaneously, and then just we need to place one at the top of the other one, and thereby we can get the complete mold cavity. So, how we basically arrange the patterns when we are positioning the mold flasks at the top of the other, that means when we are positioning the cope flask at the top of the drag flask. So, we can achieve that with the help of these dowel pins that are shown over here. So, those dowel pins facilitates accurate positioning of the cope and drag flasks. So, this is the drag flask. At the top of that we have to place the cope flask, and if it is not positioned properly, then there will be a mismatch along the parting line, and there will be no option other than scrapping the solidified object, because it will lose its dimensional attributes which are necessary to subject it to the in service conditions. Okay. So, now we will talk about the match plate pattern. So, this is a match plate pattern where the cope and drag hub of the pattern are basically mounted over a plate, and often these match plate patterns are associated with the gating and gate, runner and other geometries already created within the match plate itself. So, there is no need like we have discussed in case of single piece and two piece pattern, that we need to separately create the sprue, runner and ingates by manual operation or by other means within the mold cavity, but here in case of match plate pattern we can get the complete mold geometry at once, when because all those are etched within the match plate itself. So, this is also useful for patterns which need support, which are also for the patterns of the objects which have complicated contours and also thin sections, where effective removal of the pattern becomes difficult, or also because of the thin sections and the fragile pattern material, they can they can also face failure during sand ramming over on the top of it. So, that is why those instances can be saved by using match plate pattern. Okay. So, now we will talk about cope and drag pattern. So, these are very similar with the loose piece pattern, that two piece pattern that we have discussed just before. However, the difference is that in this case the cope and drag pattern are often analog associated with the getting geometry also. So, that is why at once when we assemble both the halves of the molding fluxes, that means cope half and the drag half, we get the complete molding geometry at once. So, so that is why it is also useful for very large castings, because in that case the patterns are also quite heavy. So, patterns cannot be handled by one single operator. So, that is why it can be done separately for the cope and drag halves, and then they can be assembled. So, then we will talk about the loose piece pattern. So, some patterns, usually single pieces, are made to have loose pieces to enable their easy withdrawal from the mold. So, for example, the typical case, if I need to make a component like this, say it is like this. Okay. So, in that case, so you can understand that it becomes very difficult to remove the sand from the mold flask, remove the pattern after ramming the sand in the mold flask if they are of single piece. So, what can happen? It can basically cause damage to the nearby area. So, it can cause, say, if we just want to remove it one piece, then it can cause a cavity within the mold much bigger than that is what needed, that is what is anticipated to get the desired geometry of the cast part. Rather, if we can make a loose piece pattern, so if we can separate, say, part A separately, and then we make it in multiple pieces, say part B and part C, then we can effectively remove these patterns after ramming of the sand in the mold and without damaging the mold cavity. So, this is the essence of loose piece pattern. And then there is a type of pattern which is also called sweep pattern. So, why they are called sweep pattern? So, you can typically understand from this schematic. So, you can see the sweep pattern is basically useful for axisymmetric shapes, when we can basically revolve the pattern within the mold cavity, so that we can get the 3D geometry of the mold cavity, 360 degree geometry, and thereby we can also save a lot of time and also cost of pattern material, and we can achieve the desired mold geometry, but this is only suitable for axisymmetric shapes like shown over here. And then the gated pattern. So, gated pattern you can see here. So, here we can cast at once 1, 2, 3, 4, 5, 6, 7, 8. So, 8 components, say these are basically connecting rods, those can be cast at one go by preparing one set of molds. So, that means and also the benefit is that all the gating geometry, that means sprue, this is the runner, and also the ingates to individual components are mounted in one single pattern. So, so simultaneously we are getting multi cavity parts, that means multiple parts can be manufactured by one casting cycle, and also all the getting geometries are attached with the components. So, that is why we need not to create any functional parts of the mold cavity separately after utilizing pattern for the mold making. So, this is the usefulness of gated pattern. So, after that we will talk about the skeleton pattern. So, skeleton pattern is a kind of pattern which is useful for very large castings. So, in this case basically we do not create a complete pattern, that means complete replica of the cast object, rather we create a wireframe kind of a model, that means which provide enough structural integrity to that large pattern for useful for the large castings, and then we basically achieve the rest part of it by within the we create the cavity, rest of the cavity within the mold itself, after getting the skeleton made with the help of the skeleton pattern. So, so this is useful for very large castings. And then there is a case of hollow board pattern. So, hollow board is a wooden board used to support a pattern during molding. So, it acts as a seat for the pattern. So, in the former case the hollow board is provided with cavity corresponding to the shape of the pattern in which the pattern is seated for molding. So, where this follow board pattern is useful. So, follow board pattern is useful when there are some intricate geometries in the cast part that are needed to be achieved. That means, there are some overhang parts. So, that otherwise can be difficult if we are going to make them by single piece or loose piece patterns, because there is chances of damage during ramming of the molding sand. Rather, in this case, when if you use follow board pattern, then the follow board acts as a support to these overhangs present in the pattern, and also so that it does not experience failure during the ramming process itself, which can otherwise damage the pattern, and in turn it can also damage the design attributes of the cast part, which is intended to be developed out of the melting casting route. So, then so now we have discussed about different kind of patterns. So, now we will discuss about the pattern allowances, but we will continue with the pattern allowances in the next class. So, we are stopping for this class now, and we will start soon. Thank you.